One, one, two, three. Okay, perfect. Yeah. So let me try again. Welcome to Iron Beetle, a show about a distributed database for financial accounting. And when I say distributed database, I must notice that it is distributed not in the sense that it is horizontally scalable, but it is distributed in a sense that it is highly available, which is actually fun. I mean, like, you run these 6 replicas, each replica runs its own database, but you actually are not, like, using all of the cores on all the 6 machines for processing. Actually, it turns out the fastest way to do this is to use just a single core for the CPU and rely on other replicas just to provide availability and data durability in case if 1 or 2 or 3 computers just crash completely. Okay, yeah, and the name of the database is Checkable, and today we'll get back to our databases. If you remember, last couple of times we did a crazy thing where we tried to like write our own code review tool. That code review tool is still in review. So hopefully we'll come back to that later and see how it goes. But for now, we are back to our databases. And today I want to share my screen and take a look at our awesome to-do list and see what is our topic which we have yet to cover. And yeah, I remember correctly, that topic is client session. So what the hell is going on with client sessions in Tagavital? The story is this. Tagavital uses static allocation. So we always have a known fixed upper bound for any amount of resources. And that creates a conundrum. Like, what happens when we are receiving more requests then we have like computed the upper bound. Like it seems like there is a paradox. It seems like, you know, there is like this fundamental variation of like how many requests are we getting, which should prevent us from just statically allocate all the requests. And the solution here is this. First of all, we say that there is only a fixed number of clients that can be connected to target middle cluster. We say that, hey, like there is like 100 clients. And if you want more, then you need to kick one of the clients out. And that seems like, you know, very restricting, like, you know, just 100 clients, that's like tiny. But as a reminder, when we think about the client for Tagabitl, we don't think about, you know, the actual mobile phone that does the payment. We are thinking about the API gateway, which aggregates many individual payments, many individual transfers into a batch of transfers and sends a whole batch. So yeah, that's like our client. And for those kinds of things, like it's totally reasonable that there is like, you know, dozens, maybe low hundreds of them. So that's how we get a static limit for the number of clients. And then we say that each client can have only a single request in flight. And that's basically it. There is a fixed number of clients. Every client can have at most one request. And that's why the total number of requests is bounded. So today we'll look at how the cluster actually tracks which clients are part of the cluster and which clients are not part of the cluster, and how it tracks that the client does not sneakily submit more than a request. And let's actually start with the second thing. Like, how do we know that there is only one request in flight? And that's like stupidly beautiful and simple. Well, it's not stupidly beautiful. It is like smartly beautiful and stupidly simple. Let's go to our message header and look at the request. And in the request, there should be extra checksum, which I am not seeing. Okay. Am I wrong about how it? Okay, yeah, this is it. So, as usual, a request is a message, so it carries two checksums. The checksum, which covers the header of the request message, so that we can correctly parse it out of the network, and a checksum which covers the body of the request. So that, so that we can ensure that CRC32 didn't mess up our message. But there is another, like the third checksum. And that is the checksum. Okay, so, well, actually, okay, so, this actually works differently. So, I thought that each request carries a checksum of the previous reply. And that way you actually cannot physically submit a request before you received a reply to the previous one. But here it seems like that is not the case, and we actually just hash chain the requests themselves. So that means that the code to prevent duplicate requests should be somewhere else. Okay, that's curious. Okay, so as you can see, I don't know how this code works, so this makes this episode way more interesting for me. Okay, but yeah, basically that is the idea. Only one request in flight. And I guess what I should also show here is how we identify a particular client, and this is it. So the client is just a U128 random number. This is like a large number, but this allows clients to generate their GIS independently. Because what we could do is that we could say, hey, like each client has like some like U32 ID, but then we would have to have some sort of like central database to actually assign those ID numbers. And I mean, Tagebeetle would be ideal database for assigning for like stored encounters, but like, we actually want to talk to this database. So what we do is that we allow each client to generate its own ephemeral ID purely random. And because the state space is so large, the probability that the two clients collide by accident is negligible. Okay, so let's see how it works. Oh, well, okay. Before we see how it works, I should also cover these like register operation. Because again, the idea here is that the cluster has only a fixed number of clients. So if like one more client joins, we need to be able to kick some older client out. And that means that the cluster needs to maintain the set of the clients which are currently logically connected. I emphasize that the connection is logical. So we count the connection not when we have like an actual TCP connection there, but when the client believes that logically, when the cluster believes that logically a client with a particular ID, with a particular random 128-bit number is part of the set of the clients of the cluster. And the way the cluster gains this logical knowledge is through this register request. So when a new client joins the cluster, the first thing it does is that it sends its a register request. Okay, so now let's actually finally look at this. Register. Okay, so this is the entry point. Let's see where it is called. Okay, it is not this. Okay, so this is the callback for register, but where is... let's see. Okay, yeah, so this is, okay, this is it. So on the left, we see the Z client, which is kind of like just a library, like internal library for the client. On the right, we have a C client, the actual code which is used by our language client, by like Python client, Java client, and all that stuff. And here we see that I've lost it. Okay. Here we see that when we are initializing our client, the first thing we do is that we fire out this register request. So we go and say that we are submitting a register with all default fields. So in particular, at that point, we set parent to 0. Okay, let's see replica side. So again, this is going to go through on message. Then this is going to go through on request, because register is a normal VSR request. It's not like special VSR operation or anything. It's just normal, hey, please pipe this through consensus, pipe this from state machine. So on request, we will convert this request into prepare, yeah, this is where this happens, and there we will pump it through consensus and execute. But before execute, let's see what is a special handling for the request. And yeah, so like this is a normal VSR operation, but also this is not operation that is handled by the state machine. This is operation handled directly by the VSR protocol. So while all the normal operations, they go through customizable state machine prepare, these service messages of the protocol themselves, we handle directly. So here we just want to inform the client about the supported batch size. So I don't think I've covered batch size here, but basically this is a small thing to reduce memory usage for development. So TigerBeetle allocates everything statically. That means it needs to allocate data to handle batches of 8,000 transfers. And you actually need quite a lot of memory to handle a batch of 8,000 transfers. It's not for the batch itself, but rather because 32 of the batches are aggregated in the in-memory table. So the size of the data we transfer in bulk from random access memory to our storage, to our disk, is batch times 32. If you have 8,000 in a batch, that means that you have 500,000 in a table, and that actually adds to a significant amount of RAM. So if you want to reduce memory usage, you could say that, hey, this cluster supports only this batch size. And then you can say, okay, I'm running a small cluster, only 100 requests per batch, and then you reduce your memory usage. So the clients upfront do not know this limit, so the replica has to tell the client about the size, and that's exactly what is happening here in this prepare. Okay, so this is it. And then we, like, after we go for normal consensus, we get to execute. And here again, there should be, yeah, there should be separate case for executing the register creation, because it is not executed by the state machine. It is executed directly. Okay. And I'm actually missing, where are we adding I'm missing where we, okay, is this it? Because we should be adding our client to the client sessions at some point. And we are, I don't see where we are doing this. Okay. Okay, yeah, this is it. So we first execute, and then after, and actually execute on like that's the logical execution. So copying the batch size to the result, but it doesn't add to this client session structure. And this like op compacted, I think we'll take a closer look at it slightly later, because that's interesting. So, but let's now look at the heavy case. So we are in the register, and we are going to update our client table. And you might be client session stable, and you might be like wondering like why, like, there's like code which executes register, but you actually update client session afterwards. And the reason is that because we actually want in our client session, we actually want to store like information about the last reply we've sent to our client. So let's see how this works. We have our reply. In the reply, we have really commit number. What is the session number? I don't know what is the session number. Okay, so this is this is curious. So I don't fully understand what's happening here. Okay, so let's dive in. Okay. What is session? Client sessions put. So client sessions. I wonder why do we need client session? Why can't we just use like client ID to say which session is that? Okay. How do we look up this data from client sessions? Okay, yeah, because you see, like when we get, we use full client ID, so U128 to look up the client. But when we put, for some reason, we only put like short U64. Okay, so this is still pretty much log war for me. I don't understand what is happening here. So let's see, execute op. Okay, okay. I mean, I knew that I don't fully understand how client sessions work, but I wasn't realizing the extent of the absence of my knowledge. Because okay, why do we need a session? Okay, well let's assume that we need session. Okay, so this part this part I understand. We have fixed number of clients. So if n+1 client tries to join, we need to decide whom to kick out. I mean, we can't just reject the new client, but that actually would be bad because probably the new client is more important than the old client because the reason why we have a new client is that some old client crashed and was restarted and generated new client ID. So we want to kick someone out. And here we need to figure out deterministic algorithm for kicking this out. So okay, this is the session that we removed. And then we add a session and we are basically done. Okay, so let's see how client sessions work because okay, I'm confused here. Like this like, I mean, I understand that the client sessions hold for each client ID the header of the last reply we sent to the clients, but I don't understand like the session numbers. Okay, so we are going to store entries by client, which is a hash map from client ID to an index of entries. So presumably we have an array of entries for like every of our clients. Okay, yeah, that makes so actually okay. So actually, it's kind of like not okay. It is more and more confusing. Now we have three identities for a particular client session. One, which I understand is like client ID. Another, which I oh, by the way, is this actually sufficiently live? Because I'm not sure. Okay. Um, Another, which I don't understand, is the session. Like, why do we need it? And then there is like the third identity, which is kind of like technically is like we are like physically in memory. This entry is situated. Okay, let's see what do we do with this stuff. Okay, when we allocate stuff, then we allocate clients max for our hash set. That makes sense. And then we allocate the entries themselves. That also makes sense. Okay, when we delegate, also just delegate stuff. Reset. Okay. Then encode size, decode size. Okay, this is this makes sense because like the set of connected clients is a state. So when a replica crashes and then restarts, it actually needs to remember the set of connected clients it has. So at some point, and I mean, for the clients which registered within the current checkpoint, that's easy. You'll get those register requests again when you will be replaying your log. But we need to remember past clients, the clients which joined the cluster before we checkpointed. So when we checkpoint, we actually need to save the full set of our clients. And that's actually what this decoding and encoding does. It like stores the data on disk. So let's actually see like to like fully understand what are the actual bytes, where is the data, what we are storing on disk. Because I mean, we can have anything we want in memory, but what actually matters is what is durable. And then for each entry, we just store this entry, which stores, I think, again, header and session. Interesting. We actually don't even store the session, just the headers. Okay, this is curious. If we don't store a session, like then why we are okay? Yeah, no. We are storing the session because we are doing structure array on disks. So first we write all the headers because all the headers are nicely aligned, and then we write all the sessions because the sessions are again nicely aligned, and that kind of like maybe means that we actually should store entries as like headers and sessions to kind of like unpack this in meat, but that like is a detail. Okay, well, and the get is similar. Okay, so far so good. We store and oh yeah, important thing. We store a reply header. So the last reply we sent to the client and the session number. We don't store the client ID, but the client ID is a part of the reply. So we actually store this data implicit. Okay, now if we want to get a client by its ID, then we look up like the index in our hash map, and then we get it out of our entries array, we assert that the session is non-zero, but we are not otherwise using the session. Okay, return the entry, perfect. Get slot for client. Okay, this is also okay. Let's mark this as a question mark. Actually, while we haven't forgot, let's in execute op there was this op compacted, which I also wanted to come back a little bit later. So let's leave some breadcrumbs here. Okay. So I don't understand this get reply slot business. Okay, put again, like given that we know session, it should be relatively easy. So we look whether we already have a client. If we have a client, we assert that the session is the same. Okay, maybe this is why we need sessions. Maybe this is what we need to prevent clients from, say, registering twice. Although, I mean, we are not actually preventing this. It is just a assert, so it's kind of like just double check. Okay. Otherwise, we store the new session. We return reply slot, and reply slot is the index of this thing. Wait. Is this actually okay? So no, okay, I don't understand. So if we okay, yeah, no. So I was worried that entry index is somehow dependent on our hash map, but no, like, you know, if we need to allocate a new entry, then we allocate it in the first non-empty elements of entries. And that actually tells me a little bit about like why we need reply slot. I think we are also going to store the actual replies to disk with bodies. So client session stores only the headers, and but we'll also be storing replies. And obviously, like, you know, you need a place to store reply at, and that's going to be the index in the client session table. This makes sense. So if we get slot for a client, yeah, that exactly is. Still, why do we need sessions? Okay, it is completely mysterious. Okay. Then we look at that code where we want to kick one of the clients out to make room for a new client. So what we do is that we find the header like with the latest commit message. So we kick out the oldest client, which makes sense. Okay, and then if we remove, then we unflip a bit, where is, okay, yeah. We unflip a bit and we zero out the entry. Okay, that makes total sense. But it's okay. So I think we actually are not using sessions anywhere. Like, we use sessions only for assertions. So session is essentially the commit number for the register request, and that's literally it. There is no other reason. Like there is no physical reason for sessions to exist. Let's get back to the replica size. And well, yeah, okay, so yeah, it is some extra validation. So like, you know, whenever we commit, we actually commit ahead of our session. So probably session could just be named like register commit or something. Oh, actually, okay, so this okay, yeah, this is just a bug. Okay. Don't. Yeah. I kind of okay. Yeah. I was okay. I officially don't get why we use client sessions like this session number. Like why we use client sessions, I understand because it feels like this session numbers don't buy as much. I mean, we do need to like we can add a little bit of an extra shorts here and there, but then we also need to protect from clients messing those up. So perhaps it would be simpler to not actually use session numbers. Okay, actually, okay. Oh, what is this session 0? Is okay. This is for pulses. Okay, so I think this gets us through the request through the register flow. And now we can see how we should be using this request. Because I think like basically the reason why we went to the great lengths to maintain this state is to be able to say, hey, client, you do not have an active session, so could you please go away and re-register yourself? And I think this is where it should be happening. So there's like a bunch of syntactic checks here and there. And then I think it's going to be duplicate. Oh, okay, so I realized that there is one thing we have to cover, and this is upgrades. Because upgrades are awesome, like really, it's my favorite part of Sagabito. But that is for future. Okay, so I think okay, yeah, here. So we got a request, and we go to our sessions and say, hey, is there a client corresponding with the session? So if it is not the case, it might actually be that the client is trying to register itself. So then we shouldn't ignore and we go to the path which we have just observed. Otherwise, okay, this is okay, so oh, this is okay. This is. I mean, yeah. I imagine this was found by Wolper because this is tricky. So, like you know, there was a cluster, and there was a primary in this cluster, and the primary received a register request, and the primary committed this register request and then crashed. And then the cluster is restarting, and the new primary got that register request from the old primary. Like no, due to like this continuous protocol, which does not allow you to lose the committed messages. But the new primary haven't yet executed this request. So like we actually should we shouldn't be saying to this client that hey, you are not registered to the cluster. You are registered to the cluster. It's just that we haven't yet got this. So here we just ignore. And in the normal case, yes. So if a client knocks to us and we do not know about this ID, that means that this client got evicted. So we send an eviction message. Okay, so the happy case. We have a client session. If it was register, I guess we will check that it is like duplicate register. And here are like those two checks that kind of like bugs me. So we like check that the session is valid, because I mean, if the client changed its session number, then something's gone wrong. But also like it's a client, so we don't actually want to crash like the entire cluster here. So we just like flag it as an error and send an error message to the client. And oh, actually, okay. So maybe this is where we need a session. So a client. Well, no. This cannot. Okay, this is also this. Wait. Okay, so no, this is a client bug. So this definitely cannot happen. But it says that this actually can happen. Okay, so I don't understand. This also should be client bug. Client A sends an operation register to refresh cluster A1. Cluster prepares and commits A1 and sends a reply A. A receives the reply to A1 and issues a second request A2. Client marks our client okay. Okay. Now I see why we need now I see why we need session numbers, and that is pretty this is pretty horrible. So we can get like messages can be replayed. So what could happen is that cluster received the register request. It assigned the session number, and then a lot of things happened. A lot of other clients joined, and we actually realized that here, actually, no, we are going to kick this client out. But then that old register request gets replayed, and well, it's not okay. No, I don't understand. Let me read it again, but now quietly so that I can actually think about what I'm reading. Okay, no. Yeah, okay, yeah. Oh, okay, so this is tricky. So actually, it is possible that like the same client registers twice in the cluster with different sessions. So if we allow for replacing the network, so imagine like you send register message to a cluster, and you register to the cluster, and then a lot of time passes, the cluster registers a bunch of other clients, you get evicted. But then your old register request with the same ephemeral client ID is replayed. And because the cluster evicted all the old clients, it doesn't have memory about the old clients. It doesn't know that the request is replayed. So it registers the client again. And this creates a problem because now this same um, client ID actually has two different sessions. So essentially, like the cluster absorbs time travel. So there was it first, so it gets a register request, and then it gets like a normal request, which actually it seems like it originated before the register request. And normally this cannot happen because we hash chain all the client requests, but the register request doesn't hash chain. Like the register's request parent is 0. So yes, we cannot detect it, and for this we need session numbers. Okay, yeah, this I think makes sense to me. Okay, so where are we at? Okay, I think we are at the point where we understand how clients get registered with the cluster, and understand that if you are unknown to the cluster, your request isn't processed, and instead you get a rejection message. Okay, that makes sense. Okay, now I want to briefly check what's up with the parent checksums, because I thought that for request you do want to include the checksum of a previous reply, but maybe okay, I think I got it. Or maybe I didn't. Or maybe I got it. So in client sessions, we store for each client the previous reply we sent it. Okay, no, I don't get it. I don't get why we are using the different thing. Okay, when we are sending the reply, what are the checksums? We set the request of a checksum, which makes sense. Okay, so now on the client, then we receive a reply. On reply. What happens here? So we validate the checksum. We say that request in flight is now. And okay, the context of this here. Okay. Oh, okay. Okay. Now I get it. So it's I was wrong twice. I mean, like this is embarrassing. Like this is same field, and I was wrong twice. So the parent is not the checksum of the previous request, and it is not the checksum of the previous reply, but rather it is the checksum of the prepare. So it is called context. Okay. Or, okay, I'm not seeing this. Reply header context. Okay, I'm not seeing this. We are not sending context here. Is it a horrible bug? Our context our contexts always 0. Reply context. Oh, okay. So, oh, okay. Okay. I'm confused. I think I've made like infinite mistakes about this field. Okay. See, so this is our reply, and then we say that the context is the checksum, including the checksum of the reply. Okay. And then we compute the checksum again. Okay, I'm super curious. Let's see send reply to client. Why do we set message again? Oh. Oh, this, okay, this is, cold path. Okay, so I think this is all about the view numbers. Because in reply, we say as a view, we say prepare view. Okay, so actually, okay, so, but, okay, first of all, but it is kind of like a checksum of the reply, so that's good. So so actually this is, okay, this is preceding reply. This is not preceding request. This is the checksum of the reply. Well, I mean, let me double check, but okay, so context is, yeah, we calculate the reply. Okay, this is mildly confusing, but I get it now. So this is the thing. We need to inform the client about the current view number, because the client wants to talk to the primary, and for that it wants to know the view number. And the nice way to inform the client about the view number is to include the view number in the reply message. But the thing is, view number is kind of like floating thing. You might commit a prepare in one view, but then that replica isn't able to talk to the client, and it has to, the next replica has to send this reply, and the view is different. So we need to say that the client, hey, kind of like the view is different. So the natural way to do this is just to flip the view in the reply message, but that actually breaks the checksum of the reply. So that's why we kind of like computed first with deterministic view, which is equal to prepare, and then we send message with a different view number. So when we in the client set the parent, it is a checksum of the reply, but like a checksum of a reply with a fixed view number. Okay, yeah. Now this makes sense. Okay, I think this is all about client sessions. The only thing I want to show once more here is who calls those like encode and decode functions. So we understand how client sessions evolve when clients register with the cluster, like, you know, someone gets evicted, someone gets appended, that's fine. We haven't shown the call sides of this encode and decode. And again, this is happening, this will happen in checkpointing process. So like we kind of covered this a bunch of times before, but right now I just want to like very concretely step through how it works. Okay, so let's see who calls client sessions encode. Actually, a lot of things seem to call this encode. Well, I don't want. Okay, probably it's going to be, okay, yeah, this is lowercase. Okay, so this is part of the checkpointing process, as I promised, inside replica. So we encode checks. Okay. So let's maybe reiterate again, like the machinery here. So like the root state of a checkpoint is a superblock. Superblock contains pointers to other blocks on disk. It's essentially like, immutable persistent data structure. So the way we encode things is by using linked lists. So we convert a particular data structure which we want to save at checkpoint into an array of bytes, then slice that array of bytes into chunks of our block size, which is 0.5 meg, and then join those blocks into a linked list. So like in the header of the block, we store a pointer to the next block. And that is machinery we use for all like extra bits of data we need to store in the checkpoints, including the client sessions. But client sessions are actually small. They are guaranteed to fit into a single chunk only. So that's why kind of like, in general, you should iterate your encoding across multiple chunks, but with one chunk, we can just assert this. Okay, so we encode this, and then we call the client sessions checkpoint. And the client sessions is the so-called checkpoint trailer, which is that essentially a list of blocks. So like right now it keeps like although it splits the blocks when writing them to disk, in memory it maintains just like one flat allocated array, which is encoded. After we encode it, when we write it, we block. Do we do? Okay, I think we are not even doing an mm copy here. So we kind of like we have all those blocks in memory. We encoded our stuff in blocks in memory, and then in the loop we write each block, and we set somewhere it should have said that like, hey, this is the next block. Okay, no, it is just address of a block. Do we? I mean, it should be. Am I wrong that it is a linked list? It should be a linked list. Okay, so I guess I wonder who is block addresses. Okay, yeah, okay, this is metadata. So in the metadata, we include like the pointer to the next element on the list of the list. So in the end, once we written everything, we get the address we should get the address of the block which starts with linked list. So okay, I think it will be checkpoint super block. super block. Okay, yeah. So then we will go and we will update the super block. And yes, we in our super block, we record the checkpoint reference, which would be the address and the checksum of the last block. And that's how we restore our client sessions like when we crash, because the client sessions are stored in our checkpoint up to the checkpoint that we just read from disk and decode. And then we are replaying all the requests which are in our log, all our prepares which are in our log, and that's because everything is deterministic, because we don't rely on iteration or order of a hash map, which that ends up creating exact same client sessions. Okay, so I think there is like a couple of things we haven't covered. Okay, get slot for client, which probably we'll cover next time, and then these op compacted. Well, let's do op compacted. Op compacted. Okay, let's quickly do op compacted. I think I understand in theory what we should be doing here, but I don't fully understand this. Why do we not? Okay, so what is op compacted? So if the op is below the trigger for a checkpoint, but if op is below the trigger for a checkpoint, if we already have the checkpoint, then why we are here as well? Like we shouldn't be replaying this, I think. Okay, so let's see. So I might be confused here. So okay, so we have our log, and let's say that this op here is a checkpoint. So like everything up to this op is going to be on disk. But we only get to this checkpoint once we get to this trigger. So like when we get here, we kind of like quote start compacting the process. And when we get to the, okay. Now I got it. So now I get it. When we get to this, okay, so we want to save this op to disk. Everything that's related to this op should be on the disk. But at the point we are executing this, so we just finished processing this op. This op is in memory. It will end up being on disk only when we get to this point, to the checkpoint trigger, because we need to run compaction to actually transfer data from main memory to durable storage. Okay, that's fine. So that means, like, if we crash here, we actually restore with this state. But except that, while we are processing all these ops, we might actually manipulate the client table and client sessions. And client sessions, we actually persist at a point in time. So we do the checkpoint here, and for the actual checkpoint, we take the state from here, so all these ops we have to replay. But for client sessions, we actually do a point in time snapshot here. So until when we crash, restart, and start from this point, we shouldn't be manipulating our client sessions until we get to this point, and that is exactly what is happening here. We check that, yeah, like we should be having entry in the client sessions here. Okay, so I think that's all for today. So as a reminder, we've learned how Tagabitl keeps only a constant number of requests in flight, and that is by requiring that there is only a constant number of clients, and that each client has only a single request in flight. We enforce only a single request in flight by ensuring that we hash chain things, that the next reply that the client sends includes the checksum of the previous reply. The next request that the client sends includes the checksum of the previous reply, which ensures that, like, yeah, there's only one reply in place. And to control the total number of clients, the cluster maintains a durable hash set with all known client IDs. And if a client wants to join and the ID is not available, then the oldest client gets kicked out and the new client gets registered. Okay, so I guess that's it. Thanks for joining, thanks for watching, and next time, next week at 5 p.m. UTC on Thursday, we'll go, and I think we'll go and look at client replies. So far we only looked at the sessions themselves, like the meta information about who is part of the cluster as a client. But we also store for each client not only the header for the reply, but the actual reply itself, so that we can replay it. And that's what we'll look at next week. Goodbye.